Hi guys, my name is Dany, and I'm gonna be the academic chief for the next year. I'm one of the new ones, me and Kevin. I'm gonna be going over the practice exam, chapter 16 and 18 for the multiple choice part. I'm gonna go over the first 10 questions, and then Kevin will go over the rest of the test. The first couple questions are gonna be nomenclature. Before I start solving them, I'm gonna go over the functional group priority. So the priority, I'm gonna start with from the highest to the lowest for the new ones especially. So the highest one that we know of is carboxylic acid. Silic acid. The second high is gonna be esters. Acid chlorides. Those combine a little bit of the final part of the nomenclature. I'm just gonna combine them for this time. Acid chlorides and the amides, nitriles, aldehydes, ketones, and then alcohols. Alright, so starting from the first nomenclature question, if you want to start, there are two choices you can start counting from. Either you can start counting from 1, 2, 3, or 1, 2, 3. We know that the ketone, or in this case double bond O, is going to take priority over the alkenes. So we're going to start counting from the other side. So 1, 2, 3, 4, 5, 6, 7, 8. So now the parent chain is going to be 7 oct in, because the double bond is on carbon number 7. 3 on, because it's like a ketone, so that's how you name the ketone. Then for subs, if you remember from chapter 17, I think, to name this substituent is going to be 4 benzyl. So putting the whole name together, remember when you put it together, you start with alphabetical order. So it's going to be 4 benzyl, 7 oct in, 3 on, and this will give you as a choice E. I usually also I divide into 3 parts. So like when I'm doing nomenclature, I put parent, sub, and stereo. But in this case, we don't have any stereo, so I'm just gonna put an A. For question number 2. We're gonna know immediately that this is gonna be number 1, because it's gonna be the ketone that has the highest priority as of now. But in this case, you either can go 1, 2, 3, 4, 5, 6, and then the substituents are gonna be 1, 2, and 5. Or the other choice you can go for it is gonna be 1, 2, 3, 4, 5, 6, and using the purple method is going to give you numbering 1, 2, and 6. So this one has a higher number, so this one immediately goes out of the window. So it's going to be this one. So let's erase the purple and leave the red. So the parent chain is going to be a cyclo hex 5 enone. You don't have to put 1 in front of the on, because once it's 1, it's usually already known that it's gonna be 1. For the subs, you have on carbon number 2, you have 1, 2, 3, 4, and carbon number 4 is a phenyl, so it's gonna be a sub inside of a sub. So it's gonna be 4 phenyl butyl. And then for stereo, in this case we do have stereo. So for the highest priority is going to be this one right here, because it's connected to a carbon that is connected to double bond O. So it's going to take number 1, and immediately we know that hydrogen is going to be always number 4. Now comparing this one to this one, this one right there, this one is going to take priority. The reason being is there is this carbon which is connected to double bond O to another carbon, which makes it a higher priority than the other one, which is just connected to one bond carbons. So 1, 2, 3, 4. And this makes it an S. And guys, remember, if the hydrogen was on a wedge, you just flip it. So if this, for instance, this hydrogen was on a wedge, it'll just become an R. Just to make you guys remember. So it's going to be S. Now putting the whole thing together, it's going to be S 2 4 phenyl butyl cyclo hex 5. It's not gonna fit, so I'm just gonna put it here, enone. And this tells you it's gonna be choice number B. For number 3, again, as I mentioned before, the aldehyde has the highest priority out of all of those groups in this case. So it's gonna be 1, 2, 3. Now you have two choices. You can go either 4, 5, 6, or you can go 4, 5, 6. We'd go 4, 5, 6 on to the left because there's more substituents on it. So 3, 4, 5, 6. So the parent chain in this case is gonna be hexanal. Subs. If we're looking at subs, we have 3. On 3 there's 1, 2, 3, so 3 propyl. And we have 4 oxo. And for 6, guys, remember how we name ethers? It's the same thing. So we just take how many carbon there is. So there is 1. So it's going to be meth oxy. Now let's put it together. There's no stereo. So I'm just going to put Na for stereo. Not available. And putting the whole thing together, remember, when you want to put it in the whole parent chain, you just follow alphabetical order. So it's going to be 6 methoxy, 4 oxo, and then 3 propyl. And then the last thing is going to be hexanal. So just put it at the end. It's barely going to fit. So the answer in this case is going to be choice C. For number 4, it's going to be about aromaticity. So let me go a little bit over the rules of aromaticity. So we have 3 things. We have aromatic, non-aromatic, and anti-aromatic. So for aromatic, it's always cyclic. It always has to be cyclic. Not just for aromatic, but also for anti-aromatic. So this is cyclic and cyclic. Those are the rules to be checked. If all of those rules are checked, this means it's aromatic or anti-aromatic. Or in this case, if it doesn't follow any of them, it's going to be non-aromatic. Anyway, so cyclic, it has to be conjugated. And it has to be planar. And the last part for aromatic is going to be 4n plus 2, which is called the Huckel's rule. Now for anti-aromatic, all the rules stay the same. Instead of one of them is going to change. Conjugated, planar, and it follows the 4n rule in this case. Non-aromatic if it breaks any of the other rules. If it fails any of the rules. Also, you can say that because it's conjugated, so the carbons all have to be sp2 hybridized. But we'll see later that some of them, when they're sp3, they can donate an electron to the p orbitals and makes it count as a electrons part of the pi electrons from the benzene ring. We'll talk about it later. Anyway, so the most annoying part of these is figuring out if it's planar or not. So if something is planar, if something is not planar, usually it's between 7 and 13 carbons. So for example, if we take the cyclooctane or 8 carbon benzene rings, so it's going to be something like this. It's going to be hard to draw it. So in this case, unless the professor, Dr. Bean, says that assume that it's planar, this molecule is not planar. The reason being is because this forms a tub shape, something like that. It looks something like this, making it non-planar. And when it's non-planar, it's automatically non-aromatic. And now talking about stability of these, the aromatic compounds are always the most stable. And then you have the non-aromatic are in the middle, and then anti-aromatic are the least stable. Now going back to the question, question number 4. Looking at this compound, we notice that yes, it is cyclic. It is conjugated. It is planar. But we have one rule is that this here is sp3 hybridized atom, which is not good. However, in this case, we have an MTP orbital, and this MTP orbital plays a major role. The reason why is one of those lone pairs can donate into this MTP orbital, and the lone pair will become a part of the ring. So what you could do right here is you count this lone pair as a part of the pi bond. So let's pretend it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So in this case, how I like to do it is always divide it into assuming that this atom right here is sp2 hybridized or an sp3 hybridized. If it was sp2, then we have 8 pi electrons. If it was 8 pi electrons, this means it's anti-aromatic. Aromatic. However, if it's sp3 hybridized, it's automatically non-aromatic, right? And now you look at the difference. Which one is more stable, the non-aromatic or the anti-aromatic? And as we discussed before, the non-aromatic will be more stable, meaning the answer would be C. Alright, so for number 5, label the anion below as aromatic, anti-aromatic, or non-aromatic. So for this case, you should draw the resonance structure of this molecule. So we start with this negative charge is going to go back down and then kick off those electrons into the ring. So now we have a negative charge right here, and then the double bonds right there. So now, looking at this molecule, we wanna first of all, let's assume this carbon is sp3 hybridized. If it was sp3 hybridized, it's automatically non-aromatic. Non-aromatic. However, let's assume this lone pair is donated into the p orbital right there, the MTP orbital. And once it's donated to the p orbital, this carbon becomes an sp2 hybridized carbon. And we count 1, 2 on this one. There is 1, 2, 3, 4, 5, 6. So now in this case, we have 6 pi electrons. And now it follows the 4n plus 2 rule, meaning it's going to be aromatic. Oh. So the answer would be aromatic. So it's going to be A. For number 6, label the anion below as aromatic, anti-aromatic, or non-aromatic, as before. So for this one, we gotta look, is all the carbons sp2 hybridized? This one is sp2 hybridized. But looking at this one, it's sp3 hybridized. Again, there's an MTP orbital, then this electrons can donate inside of. So if it was sp3 hybridized, then it will be non-aromatic, Na. sp2, but if it was sp2, then you will count those lone pair right here as a pi electron. So it's going to be 1, 2, 3, 4, 5, 6. So it'll be 6 pi electrons. And if it's 6 pi electrons, it follows the 4n plus 2 rule, meaning it's aromatic. And the answer would be A. So for number 7. It's asking about the reactivity in the Friedel-Crafts with AlCl3. So in this case, you gotta remember that Friedel-Crafts will always encourage when there is an electron donating group. So faster with electron donating group, and slower with an electron withdrawing group. So in this case, when we look at all three, we can immediately notice that this group is an electron withdrawing group. And we can tell that this amide is an electron donating group. Now here there's a common mistake that happens. People think that this is going to be an electron donating group, and it is. But in this case, this NH can do it's the Lewis acid reaction, and what happens is, this is one of the exceptions that Dr. Beam puts in her notes. So this lone pair can attack the AlCl3 and forms something that looks like that. NaCl3, this is negatively charged, positively charged, and then there is this one. So this group right here is a strong electron withdrawing group, and this causes the benzene ring to be deactivated, and thus is not good reaction with the Friedel craft. So no reaction with the Friedel crafts. So immediately you can tell that this is going to be the slowest. So I put number 1. Even though this molecule is also electron withdrawing group, but this electron withdrawing group is withdrawing electrons by induction, because it's not connected immediately to this carbon that is connected to the benzene ring, right? So this will be a little bit faster, and the fastest one would be the electron donating group, which is this one. So this one will be 3. So it'll be 3, 1, 2. So the answer would be C. For number 8, rank the following compounds in order of increasing frequency in the C double bond O stretch in its infrared spectrum. So looking at that question, always when they're asking about frequency and infrared spectrum, what I like to do personally is always look at the formula. Energy is equal to Planck's constant times frequency. Using this formula, I know that the higher the frequency, the higher the energy, and the higher the energy, the less stable is a molecule. So looking at those 3 molecules, we can immediately tell that this molecule right here is going to be the most stable. The reason why is because it has a conjugated system. So this one would have the lowest energy, meaning it has the lowest frequency. So if it has the lowest frequency, this will be number 1. And then looking at those 2 molecules, usually cyclic rings that have 4 and 3 carbons have high strain. So meaning that this one will be the least stable between those 2, meaning it has the highest frequency. So this one would have the highest, and this one would be 2. So it would be 1, 2, 3, which is A. Now looking at number 9, it's just a bunch of reaction. So the first reaction is going to be HNO3 over H2SO4. So in this reaction, you always look at the benzene ring and what is the benzene ring connected to. So the benzene ring is connected to a deactivating group or an electron withdrawing group, and it's also connected to a BR. And the bromine acts as a weak deactivating group, but also allows the benzene to react, and it adds on para and ortho substituents. So for this one, you're gonna have an NO2 on one side, Br, and then it's gonna add the NO2 either para to it, either para or ortho. But in this case, we always prefer para, like it's gonna be always your major because there is less steric hindrance. So you're gonna add an NO2. If you have like 2 choices, usually like if you have like 2 boxes, well in this case it's not gonna matter because you're gonna have a multiple choice question, but usually if you have like 2 boxes, then your major will always be para and then your minor will be the ortho. So looking at reaction number 2, reaction number 2 is going to be a addition elimination. And guys, remember, there is one rule for the addition elimination reaction is you always want to have a electron withdrawing group on the para position or the ortho position. In this case, we have an electron withdrawing group on both the para and the ortho. So this is really a good reaction and fast reaction. So let me move that a little bit down so we have space. So what's going to happen is you're going to have the NO2 stays the same, and the Br would be replaced with a no minus. And the last reaction is just going to be a Williamson reaction. So that's 3. We're going to have NO2, NO2, and then OCH2, CH3. Because what just happened is that we attack this negative charge, attack right here, and kick off the Br. You don't have to know the mechanism. I mean, you do have to know the mechanism. It's important, but for this case, if you just know the reaction, it's more than enough. So the answer for this one would be D. And then for question number 10, so we're gonna start with the Friedel-Crafts reaction. So there is a really bulky group up here, right? And then we're trying to add the CH3, CO2 acid chloride. So remember, guys, this is an activating group or an electron donating group. And remember, if we have an electron donating group, it wants to add substitution to the para or ortho position. But in this case, this is a really bulky group. So the major product would be attacking the para position. So it'll be right here. And OCH2, CH3. And for number 2, you have a Clemmensen reduction reaction. And the Clemmensen reduction, what it does, it reduces the ketones and aldehydes, and just get rid of the double bond O, and you go all the way to an alkane, which is a strong reducing agent. CH2, CH3. Another strong reducing agent would be also NH2 over basic conditions. So that's the major difference, is that one of them is going to be basic and the other one is going to be acidic. So there are a couple of places where you cannot use the acidic conditions. You have to use the basic conditions. Usually this is a way where she can trick you into synthesis questions. But in this case, you don't have synthesis. I mean, she can ask you in a different way in the synthesis question, but just be sure to know it, when to use the basic conditions over the acidic conditions. And for the last one, it's going to be Birch reduction. Now for Birch reduction, let me actually go over the mechanism really quick for this one. I don't think she ever asked the mechanism for the Birch reduction, but it's good to like understand it. And because there are a couple things to know. So the mechanism. So I'm going to start if there is a electron withdrawing group on there. Withdrawing group. So let's pretend we have such a molecule. Double bond O, and then we have that and that. We have the sodium radical. What's going to happen the first step? It's kind of a weird reaction, like we're not used to it. But this is going to attack right here. It's going to form a full negative charge. And then the rest is going to form right here. Here, and then this other radical is going to be kicked on the carbon that is connected to the electron withdrawing group. And then we're going to end up having something like that. Double bond O. So we're going to form a radical right here. There's a full-on negative charge on the para position. We have a double bond right here and double bond right here, because those two radicals right here, those two radicals form the double bond. The next step is we're going to use the alcohol to protonate this negatively charged carbon. And then we're going to end up with something like that. And then we have hydrogen and hydrogen. And then don't forget the radical. The next step, what's going to happen is another radical is going to form a full-on negative charge attacking on this carbon. And then we're going to end up with something like this. We're going to end up with a fully negative charge on this carbon right here. And this is actually a pretty stable molecule. The reason being is that this can resonate. So this negative charge can come right here and kick off that right here, forming this molecule. O minus, and then O connect to a carbon. And this molecule, because it has resonance, it is stable, and this is why you're gonna have this carbon right here doesn't have a double bond on it. Compared to electron donating group, let's pretend we have a electron donating group, and we use Birch reduction. I'm not gonna go over the whole mechanism for this one, but what's gonna happen if you have an electron donating group? The molecule is gonna end up with OCH3. And then this carbon that is underneath this OCH3 is going to have a double bond. The reason being is you don't want a negative charge underneath an electron donating group, because if you have a negative charge on the electron donating group, remember, when you have like this wants to donate inside of the ring, and then there's too much negative, and then this will create repulsion, which is super non-stable. And how I remember usually for the reaction section is just, guys, remember, when you have an electron donating group, the carbon underneath it, this one, has to be sp2 hybridized. And if you have an electron withdrawing group, well, the last step is going to be protonating, so ROH, I forgot that step, negative attack here, double bond O. Compared to this one, right here, where the carbon underneath the electron withdrawing group is going to be sp3 hybridized. That's the major difference. So now going back to the reaction, those two, we know that those two groups are electron donating groups, right? Because they are electron donating groups, the carbon underneath them is going to be sp2 hybridized, right? So CH2, CH2, CH3. So it's going to look something like that and like that. So the answer for this one would be, let's see, it's not this one. It is absolutely not this one, and it's C. And for the rest of this, Kevin will take over. So, alright guys, good luck on your tests.
Hello everyone, I hope that y'all are safe and doing well during this time. Today I'll be covering the second half of the practice exam, so from questions 11 to 20, and so let's start. So for the first problem, question 11, we are given a starting material and we are given two reactions, and we are asked to choose which of the four products, as you can see here, are actually the final product of these two sequential reactions. So the first thing we need to do is we need to have a good understanding of the starting material itself. So when we look at the starting material, what we see is that there are three phenyl rings, and on two of the phenyl rings there are substituents attached to it. So these two substituents are the alkoxy group here and the methyl group here. So these two groups are known as orthopair directors, or they're also known as electron donating groups. And since they're electron donating groups, they will actually they'll donate charge to the phenyl ring that they are attached to, making it more ready for electrophilic aromatic substitution. So the question then comes, before we even do any sort of problem where we have to add multiple substituents to a ring, the first thing we have to understand is which ring are we actually going to do these reactions on. And we can easily find out the solution to that by comparing the substituents. So the alkoxy group, or the methoxy group in this case, is more of an electron donating group than the methyl group. So that would allow for this ring, the ring in the middle, to be the most activated ring, and hence also the ring where the electrophilic aromatic substitution will occur. So that means that we can treat the two rings on each side as just another substituent. They are not going to be active in this reaction in terms of the addition of the other new substituents. So let's get into it. So the first reaction involves a whole set of reagents: hydrochloric acid, carbon monoxide, AlCl3, and copper chloride. So when you look at these reagents, actually this mixture of reagents is actually a known mixture of reagents, and it's used in a reaction known as the Gadarene-Koch synthesis. So I'll just write it here. Gadarene-Koch synthesis. So what the Gadarene-Koch synthesis does is the substituent that it adds to an aromatic ring is actually a aldehyde. So if we know that the combination of all these four reagents are going to result in the addition of an aldehyde to the ring, then the only question that remains then is where exactly do we put that aldehyde on the central ring. So when we look at this, we know that since the alkoxy group is a ortho-pair director, there are two possible positions that we can put this in. So when we look at our answer choices, actually, we find that the aldehyde group for all the possible answer choices are on this carbon, right? And that matches with our idea of the methoxy group being an ortho-pair director, because these two positions, the ones that I've circled here, are actually in the pair position relative to each other. So that means that we can add the group, the aldehyde, to this position right here. So I'm just going to write it right over here. So that's the first reaction. Now the second reaction involves the use of sodium cyanide in acidic conditions. So automatically we know that the sodium cyanide, since when we actually add it to the reaction mixture, the active component of the sodium cyanide will actually be the nitrile component, or the CN component right here, which I will put in just a sec. Yeah, this cyanide component. So basically we are going to have to add we're going to have to find a way to add this to the material. So it might be tempting to just initially put the cyanide on the central ring, but what we know is that with aromatic rings we can't just add a nucleophile. Even though the cyanide ion is a very strong nucleophile, it will not attach to the phenyl ring, because that will break the aromaticity of the compound, and the aromaticity of a phenyl ring usually gives around 30 kilocalories of resin unstabilization. So we would be losing that, and it's not energetically favorable. So we will instead, we're going to have to find a new place to add the cyanide ion. So actually, since we can look at the aldehyde component here, and if we do that, what we find is that this carbon, the carbon of the carbonyl group right here, that is actually a very electrophilic place to for the nucleophile, that is the cyanide ion, to actually attach, since this will allow for, since it's a very electrophilic region. So that's going to happen, and when you add that cyanide ion, so let me just try it right here. So once it attacks the carbonyl carbon, the electrons in the pi bond are going to go up to the oxygen atom, and we will get a negatively charged oxygen with the cyanide ion attached. And now since we have that negative charge, let me just, so once we have the negative charge on the oxygen, that oxygen can easily be protonated, and what we're left with is actually choice B as our final answer. And if we look at the other answer choices, we can see that even so, for choices A, C, and D, they all have the aldehyde, but that aldehyde doesn't have the cyanide group. And for A and D, they actually have the cyanide group attached to the ring directly, which, as I mentioned earlier, is not energetically favorable. So that is why we are left with B as our final answer. For question number 12, we are given another reaction problem where our initial product is a carboxylic acid, and we are given 3 sequential reactions and we're asked to find the final product. So let's take the step-by-step approach and go through each reaction at a time. So for the first reaction, we're adding thionyl chloride, or SOCl2. And when we do that, when you add thionyl chloride to a carboxylic acid, the OH group essentially leaves and you're essentially left with a acid chloride. So when I draw this out for reaction number 1, what we are left with is so we're left with an acid chloride. And then for the second step, just change the color. We are adding lithium tritert butoxy-aluminum hydride, the second reagent. And when you look at this reagent, you might be, tempted to think that you can use it in the same way as you use lithium aluminum hydride. But if you compare lithium aluminum hydride and this reagent, what you'll find is that there are actually considerable differences in their reactivity. Lithium aluminum hydride is probably one of the strongest or the strongest reducing agent that you will find, and this reagent actually is way tamer than lithium aluminum hydride. And it's known that especially if you react this reagent with an acid chloride, you get a aldehyde. So when we do that, when we draw out the second product, the second part of the reaction, we get, fix that, we get the aldehyde. And now on to the third part of the reaction, we see that we have these set of reagents for the third reaction. And when you see these two sets, these reagents are actually used in a reaction known as the Wolffe-Kishna reduction. Wolffe-Kishna reduction. So what it does is essentially it does a deoxygenation of the carbonyl carbon. So essentially, I'm talking about this carbon right here. So when we apply the Wolffe-Kishna reduction to this part of the reaction, what we find is that this oxygen leaves and we are essentially just left with an alkyl group. So that is actually C. for question 13, we are given a phenyl ring with several substituents attached to it, and we are asked to find the final product for the sequence of reactions that are shown here. So when we are going about trying to do this problem, we need to first understand the substituents that are on the ring. The first one at the top is the methoxy substituent, and adjacent to that is an alkane. And at the bottom of this ring, there is a alkane which actually splits out into 3 methyl groups. And so for our first reaction, we are adding the Jones reagent, which in this case is prepared using the 2 reagents that are given at high temperature, 100 degrees Celsius. So when we use this reagent on a phenyl ring, we might be tempted to oxidize both of the alkane groups that are attached to this ring. But what we need to understand is that for an oxidation of an alkane on a phenyl ring, we have to focus on the benzylic position, because mechanistically that's where pretty much all the action happens. So for the straight chain alkane, the benzylic position is right there, and for the alkane at the bottom, the benzylic position is pretty much at that carbon, because again, just to reiterate, the benzylic position is the position of the carbon that is adjacent to the phenyl ring. And so when you look at these 2 benzylic positions, the first thing that should come to your mind is that this benzylic position is actually not completely substituted. So what I mean by that is that not all 4, so it's not completely attached to 4 different substituents that are not hydrogen. In the case of the bottom alkane, that benzylic position is completely occupied, completely substituted, because it's attached to 3 methyl groups and then 1 phenyl group. So that means that the oxidation it would be very difficult to actually have it at this position. So the oxidation only then occurs right over here. So if we do that, then we get this product. We get the carboxylic acid, because since the Jones reagent is a very strong oxidizing agent, it oxidizes that alkane all the way up to the carboxylic acid. So now for the second step, this is a little bit more nuanced. We are now trying to add a organolithium reagent to this material. So when we do that, we actually have to go through this in a step-by-step process. So when we add the first equivalent of the organolithium material, so propyllithium, when we do that, what we find is that instead of immediately attacking the carbon, which we would immediately think, because it's a Grignard, it acts in a way similar to the Grignard reagent. What it actually does is that it just deprotonates that hydrogen on the acid, and because the carbon of that carbonyl the carbonyl group is actually not electrophilic enough compared to, say, a carboxylic acid derivative like an acid chloride or an anhydride or even an ester. This is way less electrophilic than those compounds. So it makes it actually hard for the propyl group to actually easily attack the carbon at the carbonyl group. So instead it just deprotonates that hydrogen. So that's the first equivalent. If we add another equivalent, this time it actually does attack the carbonyl carbon, and okay, sorry about that. And that and a pair of electrons from the pi bond actually go up to the oxygen atom. And so now then we've added our two equivalents, and if we go back to the problem statement, we see that it asks to add H3 to add an acidic solution afterwards. So an aqueous acidic solution. So when we do that, knowing that we have these two negatively charged oxygen atoms, we know that adding H3O plus is actually going to cause this to be protonated, both of those oxygens to be protonated. So now we're almost done with the second part actually. So now this is where it gets a little bit this is where the additional that one of these oxygen groups will have to go. So when we look at this compound closely, sorry, it's a little cramped, but if we include water, so, from the hydronium that was initially deprotonated, the oxygen takes out a proton, and it gives us so right now we have a very good leaving group. And in order to actually reduce the energy cost of having that positively charged oxygen on the compound, one of the lone pairs on the other oxygen are going to go down here, and it's going to cause this leaving group to leave the molecule as water. So now we are left at this molecule. And after the removal of that proton of the remaining oxygen atom, we're essentially left with just this compound. Sorry, I know that was a pretty long explanation, but just to make sure that everyone understood what was actually going on, this is the final product that we end up for after we complete the second reaction. So now on to the third part. So let me just pull this down here to get some space. Just going to clear out a little bit of what I wrote earlier. So now for the third part, we have this reagent right here. And when you see this reagent, the reaction that should come to mind is actually the Weydig reaction. So when we add the reagent from the Weydig reaction, and actually, its resonance form is actually a ylide. When we add that ylide to this carbonyl compound, this, now the ketone, when we add it, what ends up happening is that this part right here will essentially, I'm not going to go over the mechanism, but it's going to essentially replace this oxygen atom here. So when we do that, we actually have a mixture of compounds, but the major product, there is a major product for the Weydig reaction. So when we do that, we can either have or we can have another, its geometric isomer, or its diastereomer. So we're left with these two choices. And when it comes to the Weydig reaction, it actually has a certain diastereoselectivity, or what I mean is it has a certain preference for these two, to choose one of these two products in terms of its yield. So if we look at the first product, actually, what we find is that this is actually in the Z configuration, because if we look at this double bond and we compare the substituents on either side, what we find is that the highest priority groups, the ethyl group here and this group right here, they're both the highest priority. So since they're on the same side, it's the Z configuration. If we compare these two reagents here, what we find is that they're on the opposite sides. They're not on the same side of that double bond. So that gives us the E configuration. And the Weydig reaction actually chooses this as the final product, or as the major final product, because of the fact that if you compare the E and the Z configurations, you find that these two groups are far apart from each other compared to the groups in the Z configuration. These groups are farther away. So there is less steric hindrance, and this allows it to be in a lower energy state. So thermodynamically, this is way more energetically favorable. So this is essentially the major product. So that would leave us with A as our final answer. For question 14, we are given a aromatic compound with an aldehyde substituent attached to it. And the problem is asking us to find the final major product. And so if we go ahead with this, for the first reaction, when we add silver oxide and water, this reaction is actually used in an experimental procedure known as the Tollens test, which is used to determine the presence of aldehyde compounds in a certain solution. So if we apply this actually, then this aldehyde right here is actually going to convert to a carboxylic acid. So that's the first step. In the second step, we add thionyl chloride to this carboxylic acid, and this converts it into the acid chloride. And in the third step, we're adding a diorganocuprate to this acid chloride. So when we apply that reagent, what we find is that since this, so the first thing that needs to be covered is that since this is an acid chloride, the carbonyl carbon of this compound is actually very electrophilic. And so it will easily allow for the addition of even weaker nucleophiles like diorganocuprates. So when we do that, essentially this reagent, it attacks the carbonyl carbon, and that causes the electrons to go up here to the oxygen atom, and let's just draw that out. Not enough space. So now we have this negative charge on this carbon, and what's going to happen is that it's going to, this is actually known as an addition-elimination mechanism. So this lone pair of electrons is going to go down here back to in order to bring it back down to a lower energy state, and that's going to cause this chloride group to actually leave. And so what we're left with is just a ketone. So now we are at, okay, this is an intermediate, and at the fourth step, now we are basically going to create an imine with this reagent. This is a primary amine, and so under acidic, sorry about that. Let me just. When we add a primary amine, especially to a carbonyl compound, under acidic conditions, it actually causes the, you can think of it in a way as the oxygen being removed and being replaced with a nitrogen, or a part of the primary amine that was added. So what we end up with is instead of having an oxygen being a part of this double bond, we have a nitrogen and the ethyl group attached to it. The two hydrogens that were initially attached to the primary meat are actually removed during the process, so during the mechanism. And this eventually gives us the product of D as our final answer. Question 15 is asking us to convert this thioacetal to this ketone. And so in order to go about doing this, we need to actually focus on how we are going to add two alkyl groups to this thioacetal, which can then be hydrolyzed to a carbonyl group. So we need to find out a way how to add these two groups to this compound. So the first place that we need to look is actually right here in between these two sulfur atoms, because here we can remove the two protons that are attached to this compound at that point, and we can add these two alkyl groups in lieu of these two hydrogens. So the first thing that we need to do, if we're going to remove these protons, we need a base. So out of the four choices, we have two possible bases that we can use for our first reaction. We have sodium hydroxide and butyllithium. And if we compare the pKa's of these two materials, these two reagents, what we find is that sodium hydroxide has a pKa of about 14, while butyllithium has a pKa of about 50. So we can safely say that butyllithium is a way stronger base and a way more effective base than sodium hydroxide. And since the problem is asking us to find the sequence of reactions that will convert the starting material to the product in the best yield, if we use a stronger base, the chances of having a higher yield are guaranteed. So that is the first base. That's going to be our base of choice. So then the second question that remains is, how are we going to, once we've deprotonated these protons, how are we going to add these alkyl groups? And that can simply be done through the use of alkyl halides. Since the removal of any one of those protons is going to give us a negative charge on that carbon, which can easily allow the thioacetal to serve as a nucleophile that can simply do an SN2 attack on an alkyl halide and give us both of these alkyl substituents. So let's actually work that out. For the first part, when we add butyllithium, we just extend that out actually. We have a negative charge on this carbon, and so if we use an alkyl halide, we can actually attach one of our desired alkyl groups, so the ethyl group or the propyl group. I'm just going to go with I'm going to start off with the ethyl group, and if we do that, if we add ethyl bromide, then the negative charge, the lone pair on this carbon is actually going to go and do an SN2 attack on this alkyl halide, causing the bromine ion to leave, and we get our first, we get our first alkyl substituent to the thioacetal. And if we repeat this again with another equivalent of butyllithium, and instead of using ethyl bromide, we use propyl bromide, then we can easily get to this compound. So I'm just going to add another equivalent of butyllithium here, and then propyl bromide. We end up getting propyl bromide. But still, we haven't gotten to the final product. We're almost there, but we still have to remove the thioacetal. And in order to do that, we just simply need an aqueous acidic solution along with mercury chloride, which will allow for this thioacetal to be hydrolyzed and give us the final product. So if we look at all these answers, D matches our procedure. So let's look at the other choices and see why they wouldn't work. So for choice A, we find that we have sodium hydroxide, and as mentioned earlier, sodium hydroxide has a way lower pKa than butyllithium, making it a way weaker base, and so it wouldn't produce, even if it does allow for the reaction to occur, the yield would be poor at best. So A would not be a good option. If we look at choice B, what we find is that we are using butyllithium, but if we look at the two alkyl halides that are used, we find that both of them are propyl bromide. So what will happen is that the reaction will actually give us a different product in that case. We would have the propyl substituent, we would get the ketone, but instead of having an ethyl substituent on one of the sides of the ketone, we would have a propyl substituent. So that would mean that we would have more carbons than we actually wanted. So that makes this procedure ineffective as well. If we look at the third choice, we have, this one is a little bit trickier. We have butyllithium, but we have two equivalents of it. And then we have a 1-to-1 mixture of ethyl bromide and propyl bromide. And you might be thinking that, we have all the reagents that we had also for part D, but the order that we add them matters. Because even though if we add two equivalents of butyllithium, both protons on that thioacetal will be deprotonated, but since we do have both of these alkyl halides in the solution, this gives us the possibility of producing, we can also end up with our desired final product, sure, but we will also get additional products such as a ketone with two ethyl substituents on it, or a ketone with two propyl substituents on it. Because if there are two possible lone pairs on this thioacetal, and there is both ethyl bromide and propyl bromide in the solution, then at any given instant, two molecules of the propyl bromide can be attacked by the lone pairs on the thioacetal, or two molecules of the ethyl bromide can be attacked by the lone pairs on the thioacetal. So this gives us a variety of products at the end, and so it wouldn't give us the best yield of our desired product. So this also makes it an ineffective solution. So this is why we are left with D as our final answer. For question 16, we are given a starting material and we're asked to find the sequence of reactions that will allow us to convert it to the product in the best yield. So when we look at both of these substituents, we need to first identify the functional groups. So in both of these substituents, at the bottom of the rings, we have an aldehyde. And near the top, we have, for the starting material, a nitrile group. And at the same position, but at the final product, we have a ketone. So we need to find the right sequence of reactions that will allow us to get from here to here, from starting from point A to point B. And in order to do that, we need to, we can easily, be tempted to think that if we just add a Grignard reagent, we can easily convert this this starting material to this final product, because that's all it takes, a Grignard reagent along with an aqueous workup to get to that point. But when we look at the reaction, what we find is that this aldehyde is also open game for a potential site of attack for a Grignard or diorganocuprate reagent. So we need to find a way to synthesize the final product without affecting this aldehyde group, because it remains unchanged. So in order to do that, we need a protecting group. So we need to basically find a way to retain this oxygen without it being affected, without this substituent being affected by the Grignard reagent or the diorganocuprate reagent. So that is how we can, so if we use, for example, ethylene glycol and in acidic conditions, we can easily convert that carbonyl group to an acetal. Sorry about that. So now we have our protecting group added. And so now we can easily do the Grignard reagent to add that extra methyl group that is attached to the carbonyl carbon. So if we do that, I won't go through the mechanism, but we end up the ketone, and we still have our protecting group unaffected by the Grignard reagent, because the if you think about it, a acetal is pretty much as unreactive as an ether, so, or most ethers. So this is why it can withstand a lot of attacks from reagents such as the Grignard reagent or diorganocuprates. So now for the last part, since we have the top part fixed, we're good with that. The bottom part, now we need to bring that back to a carbonyl substituent. So with just the addition of H3O plus, we get back to that compound, the desired compound. And answer choice C best matches our description. But let's go through the other choices to see why they would be ineffective. So first off, right off the bat, for choice A, if we were just to use the Grignard reagent and then some aqueous acidic solution, what we find is, as we mentioned earlier, the aldehyde is vulnerable to attack. So it would give us a different product from what there might be some of our desired final product, but it will be in lower yield because this site is also available for attack. So that crosses out A. For part B, it's asking us to, for the first step, we add aqueous solution at 200 degrees Celsius. And this does not help to set up a protecting group in any way, so that, or the acetyl, or any other way to protect this aldehyde. So it still leaves that aldehyde in a vulnerable position. So we can still end up with varying products. So this rules out B. For part D, we have the protecting group part settled. We have the ethylene glycol and the H3O plus at the end. But the problem is that we do have a diorganic cuprate, so it can still react with the cyanide to produce a ketone, but if you look at it, it has a ethyl group instead of a methyl group, and this will give us the ketone but with an ethyl substituent on the right hand side, so that is not our desired product, so that rules out D. So ultimately we are left with C as the best way to produce the final product in the best yield. So for question 17, we are given a reaction, and it's this reaction, and we are asked to find out of the answer choices that are given to us, we are asked to find out which one was an actual intermediate for this reaction. So let's actually work it out. Let's actually write out this whole reaction mechanism. So when we add hydrochloric acid to this compound, the starting material, what we find is that the protons, the lone pairs on the oxygen, are actually going to attack the proton on the HCl. So it's going to get protonated, and we find that we have protonated water as one of our substituents. Protonated oxygen is one, the hydroxyl group as one of our substituents. So the next step then is that since this is a good leaving group, this will leave, and we have a carbocation. A secondary carbocation, to be precise. And before we go on any further, just as a review of carbocations, so this is a secondary carbocation, but it's not the most stable carbocation. In the order of priority we have of carbocations, we know that primary carbocations are less stable than secondary carbocations, which are less stable than tertiary carbocations. So right now we have a secondary carbocation, and we want to move that into a more stable configuration. So in order to do that, we can rely on a rearrangement, and specifically a hydride rearrangement. So the proton that is attached to that tertiary carbon, which is adjacent to the carbocation, can easily be moved to the carbon where the positive charge rests on, and what we find is that we can actually produce a tertiary carbocation. So now that we have a tertiary carbocation, we are actually in a good position because I will just write out the benzene double bonds, the aromatic ring double bonds. So now that we have a positive charge, this allows for one of the double bonds of the, let me just actually redraw double bonds. So now this double bond can actually go and the electrons in that pi bond can go and attack or attach itself to the tertiary carbocation, allowing us to form a ring. So the reason why I actually moved that positive charge up there was because actually when the electrons in the pi bond for the aromatic ring migrated and attacked the carbocation, there was no proton actually in this position right here. So that means that when those pi electrons were moved, there was an absence of a fourth bond for that carbon, that tertiary carbon. So we're left with a positive charge, but we do have a proton here at this carbon. So we are close to our final product, but the only thing is that we need to also consider its resonance structures. Just to be thorough, when we do that, we find that if we move this pi bond up here, then in order to compensate for that loss of pi bonding electrons, the carbon right here will, so the lone pairs of that oxygen will go down here, and our resonance structure is actually as follows. So now we might seem like we're farther away from our desired product, but we can easily get from this from the second resonance structure that I drew to the final product by simply considering that earlier we had actually produced a chlorine anion. So this chlorine anion can actually come back into play at this point in the reaction. Right? If we have this chlorine ion, it sees this proton and it decides to deprotonate that carbon, causing the electrons that were initially attached to that proton to move up here and do an elimination, and the pi electrons move up there, and the pi electrons connecting the carbon and the oxygen atoms also move here to give us our final product. Now if we look at our answer choices, we see that none of the other choices, A, B, C, and E, are actually present in the reaction mechanism, but we'll just go through them just to see why they would be wrong. So I'm not putting it up here, but if you look at your problem, at the question handout, solution A has, or the answer choice A, has a negative charge on the carbon. And this is a improbable choice because that means that essentially the proton of the hydroxyl group was deprotonated, but there is no base in the reaction mixture to actually deprotonate this hydrogen. So it would not make much sense to use that as, to consider that as a reasonable intermediate. The next choice, choice B, has a positive charge on this carbon right here. And the reason why this would also be inaccurate is because if you actually go down to the, if you actually look at the rearrangement step where I did the hydride shift, it actually meant, because if we go from, it doesn't make much sense in terms of rearrangements to go from one energy position to another energy position if they're both equal in energy. And what I mean by that is, for example, in the rearrangements, I went from a secondary carbocation to a tertiary carbocation, which is lower in energy and more stable. So when rearrangements happen, you go from a less stable carbocation to more stable carbocation. For option B, we're just going from a secondary carbocation to another secondary carbocation. So it is not an effective choice to an effective rearrangement. So it's implausible that it would occur during the reaction. And if we look at choice C, we have a positive charge right over here. And so right here, oh, let me just draw it out. We have a positive charge at this carbon, the carbon which the proton is attached to. And as I mentioned earlier, this is also an improbable choice because there was already a proton at that carbon before the chain was formed. So when that when the tertiary carbocation decided to attack, well, when it was bonded to that original aromatic ring, that proton was already there. So there's no absence of a fourth bond or a fourth substituent. So that means that it's not possible for there to be a positive charge. But on the other hand, this carbon did not have a proton before the pi electrons left and attached to the tertiary carbocation to form the ring. So that means that when that ring was formed, there was no more, there was an absence of a bond. So that meant that there was going to be a positive charge there. And that's what we see in the resonance structures. So that means that option C is also not going to happen during the mechanism. If we look at option E, it tells us that apparently there was a negative charge on the, instead of a positive charge. And again, if there was a negative charge, that means that there would be an extra pair of lone pair of an extra lone pair at the top here, and our reaction, even our resonance structures don't indicate that. So that means that option E isn't considered to be possible either. So that leaves us with option choice D for answer to be D. So that is the most reasonable intermediate for this reaction. So for question 18, we have a reaction again, and we are asked to find out of the 5 answer choices, we are asked to choose one of them as being a plausible intermediate for this reaction. So let's work it out. So in the first step, when we add H plus, again, when we add acid and when you see acid in a mechanism problem as being one of the immediate reagents, you can know that one of the first things that happens is protonation. So that's precisely what I'm going to write out. A lone pair from the oxygen obtains a proton, and we have an oxonium ion. And an oxonium ion is very unstable, so it needs to find a way, so the compound at that point has to find a way to, the molecule has to find a way to go to a more stable state. So this is where the amine group comes into play. Actually, let me just erase that. It does not have an additional lone pair. So the lone pair on the nitrogen, or the amine, will attack the carbon attached to that oxygen, and it will allow for the pi electrons to go up to the oxygen. So now we just have a hydroxyl group. And actually this causes the formation of a ring. So right now we have a positively charged nitrogen, and again we want to try to remove those charges. So this is where the water comes into play. So the water will actually deprotonate this nitrogen, and in doing so it returns a lone pair to that nitrogen, and now even though this is a stable intermediate, this still has to react with, we're still in acidic conditions. So again, since there is an oxygen and since we are in acidic conditions, that means that the oxygen will be protonated by the acid present. So I'm just going to write hydronium. So if it undergoes protonation, then now we are left with an unstable positively charged oxygen. So now we have to address that charge. So what will happen is that this nitrogen will actually give one of its lone pairs and form a double bond here, which will cause this water to leave. And now we are actually quite close to our final solution. So if I'm just going to So now the remaining step really is just to, because at this point we have a positively charged nitrogen because it has four bonds at that point, so which is past its valency. So a simple way to get from here to the final product is just to use water, which will deprotonate that nitrogen and return a lone pair to that nitrogen atom, and we are left with the final product. So in examining this mechanism, we find that choice D exactly matches with our final step. So that leaves E as the answer, but in seeing the other choices, but we can go through the other choices and just evaluate why they would be incorrect, mechanistically speaking. So since we have the first choice, A, has a positive charge on the nitrogen, but there is no double bond here. So I'm referring to this compound. So it is just like this compound, but it doesn't have a pi bond between the nitrogen and the adjacent carbon. And as shown in the previous step, that nitrogen bond, that double bond, is formed when we're trying to remove that water. So it makes A an implausible solution. When we go to answer choice B, what we find is instead of we have a negative charge on this nitrogen, and we lose one, and there is only one proton instead. So what that means is that nitrogen was deprotonated. But again, as I mentioned somewhat earlier in problem 17 as well, there is no base to actually just deprotonate either a nitrogen or an oxygen. So it makes that answer implausible as well. Answer choice C has, again, this compound, but there is no positive charge and there is no pi bond between the nitrogen and the carbon. So this implies that there is a lone pair at this nitrogen, which would be wrong because that lone pair was used to form that double bond, and that also results in the positive charge. So that makes C an implausible solution as well. And also for part D, we have the starting material but with no carbonyl group. In fact, there's just a positive charge at that carbon, but there's no oxygen. So this would be incorrect because even though we do lose the oxygen during the reaction process, we don't lose it sheerly from the acid present in from the aqueous acidic solution. So that makes that answer choice wrong as well. So ultimately we are left with E as our final answer choice. Questions 19 and 20 are NMR and IR type questions. So we are given a compound with a empirical formula of C7H14O. So we are given a set of IR and NMR data, and we're asked to determine which compound best matches that data. So the first thing that we have to do is just examine the IR data, and this will give us some hints about the structure of the compound. So it says that the IR spectrum exhibits strong peaks at 2,972 and 1,714 inverse centimeters, or the wave number. So if we look at these two numbers, we know that the wave number of 2,972 is indicating a proton that is attached to an alkane. So just a CH single bond alkane compound. So then the 1714 wave number refers to a carbonyl compound. We can't exactly pinpoint which carbonyl compound that points to, but we know that there is a certain CO double bond. So these are the first indications that we have. And this is actually very helpful, because if we look at answer choices A, C, and E, all three of those choices actually have hydroxyl groups in them. And we know that the hydroxyl group has a very broad peak past the 3000s. So somewhere around the 3,500 to 3,300 region, but it's a broad region. And they're not just strong, intense peaks, narrow peaks either. So that means that we can easily cancel out options A, C, and E. So that leaves us with choices B and D. So now we can look at the Proton Nmr to help us to further, limit our criteria to choose which of the two options is correct. So before we do that, it would be helpful if we actually drew out the actual structures of both of these compounds. So let's do that. I'm just going to add the protons as well, so it'll be easier to understand the interpretations, to interpret the NMR data. And for this compound as well. So the NMR data tells us that there is the Proton NMR tells us that there is a septet at 2.8 ppm and a doublet at 1.1 ppm. So right off the bat, we can see that, if we look at, for example, for answer choice B, in order to have a septet, we need to have 6 chemically equivalent protons on an adjacent carbon atom. And if we look at this, for any of these carbons, so any of the carbons on this compound, for any adjacent carbon, so if we follow the n+1 rule, that means that there needs to be actually 6 protons attached to an adjacent carbon atom, or 6 pairs of chemically equivalent protons. And if we actually had an NMR proton and NMR spectra of this compound, we would actually be seeing quartets or triplets, because, for example, for this carbon, the adjacent carbon has 2 protons, so that means that there would be a triplet. And for this carbon, the adjacent carbon has 2 protons, so that means that there would be a triplet. And for this carbon, since there's 2 on this carbon, 2 protons on this carbon, and 3 protons on this carbon, it would lead to complex splitting behavior, which is not given to us. So that means that this would mean that choice B is also incorrect. So that leaves us with D as our answer, but just to explain why, if we look at the structure, we have 1 proton on this carbon, and then we branch out into 6 protons that are chemically equivalent. And they're also bonded to carbons that are adjacent to this carbon. So that means that since the chemical shifts are 2.8 and 1.1, it also makes sense because that refers to the fact that they're both protons that are attached to alkanes. So in that case, it would also make sense that there would be a septet and a doublet, because if we consider the protons that are attached, so the protons that are branched out here, the carbons that are branched out here, then following the n+1 rule, since their adjacent carbon atom, which is this carbon right here, has only 1 proton, that means that there will be following the n+1 rule, there will be a doublet. And that is what is given to us, a doublet at 1.1 ppm. And if we consider the carbon that has 1 proton, then if we consider that NMR spectra, it would have a septet because there are 6 chemically equivalent protons here. So following the n+1 rule, that means that there would be a septet, or 7 peaks that are adjacent to each other, that fall under that are caused by splitting behavior. So that means that it does match with those the peak splitting behaviors. And lastly, the last detail we need to cover is the 1:6 ratio of the integration numbers. So if we consider that because of symmetry, we can consider these 2 protons to be identical to each other, and these 2 sets of protons to be identical, chemically equivalent. So that means that there would be 2 of these protons and 12 of the ones that are on the periphery of this molecule. And this ratio reduces down to 1:6, which matches our problem statement. So this leaves us with D as our final answer. For question 20, we are given an unknown compound with the formula C9H10O. And we are also given some IR spectrum data and some Proton Nmr spectrum data. So when we look at the data, the first thing we need to see is the IR data. And the problem tells us that there is a strong peak at a wave number of 1,724 inverse centimeters. So from the IR spectra, this tells us that the unknown compound has some form of a carbonyl functional group in it. So if we look at all our answer choices, actually, all of our compounds have a some form of a carbonyl compound. So this doesn't help us to cancel out any of these, and I don't want to point out that a carbonyl compound is a, for example, a ester, or compared to an aldehyde, or any type of nuanced comparison in that, because sometimes due to various factors the numbers can vary. So especially when you're dealing with IR problems, it's better to have a general idea of where where any sort of functional group might be in, instead of having precise numbers memorized, because those numbers can vary depending on the molecule and its structure. But we know that since we have a wave number close to 1700, we know that this will have some form of a carbonyl compound. So then the next set of data we have to go through is the Proton Nmr data. So we see that there is a singlet at 9.9 ppm, a multiplet at 7.9, a triplet at 3.06 ppm, and a triplet at 2.84 ppm. So the best thing to do in this case is that we should probably draw out all of these compounds. So for compound A, we have a ring, an aromatic ring with a aldehyde, group, and a ethyl group, ethyl substituent attached to it. For B, we have an aromatic ring, again with a substituent that has a ketone substituent. So actually, let me just draw the protons here so we can be clear about what's going on. For C, these are all going to be aromatic rings, but their substituents vary. I apologize, this is actually supposed to be option C. Or no, this is B. Confused it, but here we have I'm just drawing out these protons because it makes it easier to interpret the data. And again, the notations here, para and meta, just refer to the positions of the substituents. So for A, the aldehyde and the alkane substituents are para to each other, so they're on the opposite sides of the ring. And for D, the meta substituents, the meta refers just to the fact that the aldehyde group and the alkane group are just two bonds away, two carbon atoms away from each other. So then drawing out lastly for E, the aldehyde group. So now we can examine all these structures, and so let's do that. So for the first piece of data that we are given, we have a 1 proton singlet at 9.9 ppm. So this should actually verify the information we were given in the IR, because that's a very high chemical shift, 9.99 ppm. So that would correspond to a carbonyl compound, either a ketone or an aldehyde. And in this case, the carbonyl compounds that were given are precisely either one of those. So that is just our verification of the IR data. And also, our NMR data actually also tells us an additional thing. It's a 1 proton singlet. So that means that if there is if there's just 1 proton, then it can't be a ketone actually, because that carbon, which is attached to via double bond to an oxygen, has to be attached to a proton as well. And in the case of the ketone, we don't have a proton attached to it. So that means that any choices with a ketone in it would be rendered incorrect. So that leaves us, that immediately knocks out options B and C. However, now we have options A, D, and E. So now let's move on with the problem statement. It asks for tells us that there's a 5 proton multiplet at 7.99 ppm. And when you think of the 7.99 ppm chemical shift, around any NMR data given around shift around 7.9 ppm or 7 ppm you can immediately think of an aromatic compound, an aromatic proton. So that doesn't give us a lot of information, but again, the integration number does. This tells us the number of aromatic protons there are. So there are 5 aromatic protons according to the integration. So that means that easily marks out options A and options D, because they have 2 substituents, so therefore they only have 4 aromatic compounds. So then at this point we could say E, but just to go through the problem statement and just to make sure that we're on the right path, we can examine the rest of the data. So when we see that let me just clear that out. So it says that there is a 2 proton triplet at 3.06 ppm and a 2H triplet at 2.84 ppm. So if you're given NMR data that's around the 2 to 3 range for a chemical shift, then it's a strong indicator that you might have an alkane. So if you have an alkane, then that immediately points out that we can see that actually here with these 2 compounds. And this also matches the integration data, because there's a 2H So again, that matches the fact that there are 2 protons for this carbon and 2 protons for this carbon. In addition, it also says that there's a triplet at those two, for those two particular sets of protons. And that makes sense because the adjacent carbon, which in this case is either one of those, has 2 chemically equivalent protons. So according to the n+1 rule, that means that there should be 3. 3 spikes for each set of NMR peaks. So the splitting pattern also agrees with the structure of this compound. So that eventually leads us to the conclusion that E is the final answer. I hope you found this to be helpful. Thank you.